Okay, so we're going to get into graphing, but before we get into graphing, let's talk about concavity and what it means to be concave up and concave down. When we're looking at concavity, we're looking at the derivative of the derivative. So we're looking at that second derivative. And remember, the derivative is just the rate of change. And so let's just go through the definition really quick. First of all, the graph of a differential function, y equals f of x, is said to be concave up on an open interval I if the derivative is increasing on I. It's concave down on an open interval I if the derivative f prime is decreasing in I. So this to me was a little bit confusing, but the picture kind of helps what they're talking about because I never thought about it this way. But if you look at this concave down picture right here, and you think about looking at the tangent lines, notice that the tangent line, as we are moving, it's decreasing. It's not as steep, right? Where if you're looking at the side where it's concave up on the right-hand side, first quadrant, and we look at the tangent line, the slopes, right? We first start down, and as we move, that tangent line is getting steeper and steeper. So that derivative is increasing. So that's what that definition is saying. To find out where a function is concave up and concave down, we need to find the second derivative. And we're going to find those values of the second derivative where it's equal to 0 or undefined. And so this is the second derivative test for concavity. We're going to let y equal f of x be twice differentiable on some interval I. We're going to look at if we find that the double derivative is greater than 0 on I, then we say that the derivative or that function is concave up on I. So concave up, it looks kind of like a upward parabola. Concave down, this happens when our second derivative is less than 0 on this I. We say that that graph is concave down. So to me, it looks like an upside down parabola shape. So it really depends. We'll find the intervals where it's concave up and concave down, but it really depends on it. Is it increasing or decreasing? And so we know that we can find a function is increasing or decreasing by looking at the first derivative. So notice that if your first derivative, come on. Hold on, my pen's not working. Okay, so it really depends on is our first derivative greater than 0? If we have that our first derivative was greater than 0 and that our second derivative is greater than 0, this is telling me that it's an increasing function, so going up left to right. And greater than 0, I think of it, it's positive, so it can hold stuff. So it's a parabola facing this way. But if you look at putting these both together, the shape that you're going to get, because it has to be increasing, would be looking like this shape on that interval. So we're going to look at the 4 different possibilities. You could have your derivative greater than 0, still increasing, but our second derivative is less than 0. So that means it would be concave down shape. And if it was a concave down shape though, and increasing, and think about it on this side, it would be have a shape that looks like this. So now let's look at what would happen if our derivative was decreasing. Our derivative was less than 0. We know it's decreasing. If the second derivative, let's say, was positive, this is concave up. So looking at a piece that is concave up but decreasing, the shape that we're going to have is like this. Looking at when our first derivative is less than 0, so still decreasing, but our second derivative is also less than 0. So this is a concave down function, but it's decreasing. And so decreasing that piece of the parabola is going to look like this. Okay, so the concavity is going to give us basically more of the shape of what's going on when we start graphing these in a few moments. But let me give you a couple more different definitions. And actually, before we did that, there was an example. So you should be able to look at a graph, and looking at the graph, give the intervals where it's concave up and concave down. So if I was looking at this graph, I noticed that this piece right in here, starting when x is a, and it starts to change direction on concavity at this value of b. So I know that this is concave up. So remember, interval notation, we use our x values. So from a to b. Then it looks like it's concave up here, so union. From 0 to e. But it also looks like it's concave up here from, looks like a sharp corner, e to h. Only piece in here that to me that looks like it's concave down is b to 0. This place where it's changing concavity, so it looks like it's at the origin here and right here at B, these are called inflection points. So points where a graph changes concavity. Are called inflection points. And these are the values which set our double derivative equal to 0. So we're going to do the exact same thing we were doing when we're finding where our function was increasing and decreasing. It's just this time we're going to look at the second derivative, find where it's equal to 0, where it is undefined, but defined in the original, and then test our intervals by plugging it into the second derivative. So just kind of what I just said, but let me just restate it really quickly. So definition, we say point C, f of c would be the y value when x is c, f of c, where the graph of the function has a tangent line. And when the concavity changes is a point of inflection, or the inflection point. So telling me that it has a tangent line tells me that it's differentiable at that value. So it has to be defined in the original equation. It says at a point of inflection, this point c, f of c, either the double derivative at c is equal to 0, or the double derivative at c fails to exist. So it's undefined, but again, has a tangent line, so it has to be, in order to be a point, has to be defined for our original function. Okay, so here is a test to also help us find where we have a maximum or minimum value, local max or local min. Before, when we were finding if a point was, our critical point was a max or min, we found out where it was increasing and decreasing. So if we found something that was increasing and then it was decreasing, we found that this was a max occurred there. And we saw that if it was decreasing to increasing, we found that we had a min there, as long as it existed in our original function. There's another test that can test to see if a critical value is a max or a min, but it doesn't always work, where this first derivative test does always work. This says, suppose that your second derivative is continuous on some open interval and contains the value x equals c. If the first derivative is equal to 0 and we plug in that value, so critical number, we plug in that critical number into the second derivative and it's less than 0, then we can say that there's actually a local max at c. How I kind of think of this is that a double derivative is less than 0, so the parabola shape is facing downwards at that c value, and so I can see that that's a max that occurs there. If we plug in our critical value, which set our first derivative equal to 0, into the second derivative and it was bigger than 0, then we can say that we have a local minimum at that value. The problem is if you find your critical value, you plug it into your second derivative and it tells you that it's 0, then this test doesn't work. There could be a max or a min there, but we don't know, and we have to go back and we have to look at our first derivative test. So this is just another method to find local extrema, local max, local min values. Okay, so putting kind of all together what we've been learning, procedures of graphing our functions. And so we've looked at graphing before a little bit with limits and looking at limits as our end behaviors. Our x value goes to positive or negative infinity. We've looked at asymptotes, vertical, horizontal. So now we're going to put that together with what we also know about derivatives to help us graph. We can also bring in some information from our algebra course to help us. So first thing, and these orders you don't really have to do, but first thing, or one of the first things you should do is you should identify what your domain is. Because if we find critical values, we need to see if it's in our domain or not. So we need to identify our domain. If you want to, you can use symmetry to help you graph. So really quickly recall, if you plugged in negative x wherever you saw an x and you got back the original function f of x, this was by definition an even function. And it was symmetrical across the y-axis. So if you knew that it was symmetrical across the y-axis and it was an even function, then we know, if we know one point, we know another point. So we know double the points. So if we know xy was a point on our original function f of x, then that point negative x positive y is also a point. So we could use that fact if we wanted to help us graph these. Same sort of idea with odd functions. Odd functions, recall, if you plugged in negative x wherever you saw an x in your original function and it gave you back the negative of your y value, this was symmetrical across the origin. So basically, if you folded your papers in force along the x-axis and the y-axis, there would be a mirror image. And again, if you know one point on our graph, then you know another point. So if xy was a point, then you would know that negative x negative y is also a point on the graph. So symmetry, if you can tell really easily if it's symmetrical, then it could help you graph, but this is something I normally don't do when I go about graphing these functions. Find derivatives. So we're going to need to find our first and our second derivative of our function. And that's because for step 3, we need to find our critical points. So we need to find the derivative and set that equal to 0, or find where it's undefined first derivative. So if there's any critical point, we want to identify the function's behavior at each. So is that going to be a local max or a local min at that critical point? We also want to find where the curve is increasing and where it's decreasing. And so that's basically how we can find what behavior is going on at that point by testing our intervals into the first derivative. We want to find our inflection points. So that's using that second derivative, if any occur, and determine the concavity of the curve. So testing our intervals on the left and right of our possible inflection points and seeing if the double derivative is greater than 0 or less than 0. We've looked at asymptotes before. So rational, that's when we have a rational function. We have variables in the denominator. Values that set the denominator equal to 0 and not the numerator, those were vertical asymptotes. And then we looked at end behaviors of the graph of rational functions to see if we had horizontal asymptotes. With that, plotting key points such as intercepts, x-intercepts and y-intercepts, and the points found in pretty much above 3 to 5, sketch the graph and any asymptotes if they exist. Okay, so that's the game plan. Need those to help us graph. Let's look at an example. And let's look at f of x is equal to x to the fifth minus 5x to the fourth. Okay, so looking at that, I can tell that I don't have any problem spots. I don't have any values of x that if I plugged in there, I wouldn't get back a real number or it was undefined. So that tells me my domain for f of x is all real numbers. We want to find the first derivative. So let's find the first derivative, f prime of x. And doing that, derivative of x to the fifth is 5x to the fourth. Minus, and the derivative of 5x to the fourth is 20x cubed. We want to find where this is equal to 0. So 5x to the fourth minus 20x cubed equals 0. Well, I notice I can factor this. They both have a greatest common factor of 5x cubed. So let's pull out a 5x cubed from both of those terms, and we'll be left with an x minus 4 equals 0. So setting each value equal to 0, each factor, I can see that 5x cubed equals 0 when x is 0, and x minus 4 is equal to 0 when x is 4. So these are our critical numbers, and we want to plot those on the number line and test to see if our values are positive or negative in those intervals. So we're looking at the second or the first derivative and plugging in numbers. So choose a number to the left of 0. So how about -1? So if I looked at x equals -1, plugged it into the first derivative, I want to see, is that positive or negative? I really don't care what value that is. If it helps us, we could think of our derivative f prime of x in the factored form, right? Because 5x cubed, I can tell right away when I plug in -1, that's negative, and x minus 4. If I plug in -1 into that factor, it's also negative. So first piece, I would get a negative number times another negative number, so that's positive. So this is greater than 0. So on the left of x equals 0, our graph is increasing, going up left to right. Choose a number between 0 and 4. So how about x equals 1? If we plug it into the first derivative, we want to see, is our number that we get back positive or negative? Well, 5 times 1 cubed, that's a positive number. All times 1 minus 4, which is a negative number. Positive times negative is negative. This is less than 0, so it's decreasing here. So since it was defined at x equals 0 in the original, we can tell that we have a max. occurs at x equals 0. You might as well find it right now. Plug it back into the original to get that point. So f of 0 was 0 to the 5th minus 5 times 0, so that's just 0. So we have a max that occurs, and we know that this is a point 0, 0. Okay, so one more value we have to test, something on the right of x equals 4. So how about x equals 5? Plug it back into the first derivative to see if it's positive or negative. Well, 5 times 5 cubed, that's a positive number. All times 5 minus 4, which is positive. Positive times positive is positive, so it's increasing. So something that decreases to increasing, we can tell that we have a min value here. So min occurs at x equals 4. If we plug in 4 into the original problem, we got what? 4 to the 5th power minus 5 times 4 to the 4th. Oops. It's 5 raised to the 5th minus 5 times 5 raised to the 4th. Did I say that right? And that gives us 0. That makes sense, right? So our point here, we have a min of 0 when x is 4. Okay, so I want to kind of put together what I have so far, and then we'll come back to and look at our concavity. But so far, let's plot what we have. So we have a point that is at 0, 0. And we knew that this was a max. We have something increasing and then decreasing. Then we had that at x equals 4, we had 0. Something's wrong. I was plugging in 5. I need to plug in 4. So plugging in 4 into my original. So if I plug in 4 into my original, that's 4 raised to the 5th minus 5 times 4 raised to the 4th. Wow, that's a pretty big number. Let me just make sure that this was inside the parentheses. Yeah, so this is negative 256. So plugging in 4 into this function. Okay. Well, I'm not going to really draw negative 256 tick marks. So let's say that this right here is negative 256. And here is an x value of 4. And so I have a point here. So it was decreasing here. And then at x equals 4, it changed directions and it started to increase. So that's how I know this was a min value. Saw that in the chat. And so I know this is a max because of it being defined at x equals 0 from my original equation. But something that increases and then turns around and decreases, a max has to occur. So now we need to figure out the concavity. And concavity looks at the second derivative. So right here we have our first derivative. f prime of x is equal to this 5x to the fourth minus 20x cubed. So let's look at the second derivative. So derivative of 5x to the fourth is 20x cubed minus, and the derivative of 20x cubed is 60x squared. So we want to find inflection points. This is values where this is equal to 0 or undefined. Well, it's defined everywhere. So we just have to worry about when is this equal to 0. I would probably factor this. We have a 20 and an x squared in common that we can pull out, and we'd be left with an x minus 3 equals 0. So at 20x squared equals 0, this is when x is 0, and x minus 3 equals 0 when x is equal to 3. So we want to take this and we want to test our intervals. So we want to look at on the left and the right of these intervals. So our two numbers are 0 and 3. So plugging this into the second derivative, again, if we're only worried about when is this positive or negative, so we could think of the second derivative in factored form, 20x squared all times x minus 3. So if we choose a number to the left of 0, so how about x equals -1, plug it into the second derivative. Well, -1 quantity squared is positive times 20. So that first piece is always going to be 20. -1 minus 3 is negative. So I see that this is less than 0. So this has to be concave down. So if I go back to this graph, until I hit 0, I'm concave down. My graph looks like this. So let's look at what's happening after 0 and before 3. So choose a number between 0 and 3. So how about 1? If we plug this into the second derivative, well, we have this 20 times 1 squared is positive, all times 1 minus 3, which is negative. So this is less than 0. This is concave down. So notice here, it's concave down. So it's still going downwards, concave down this shape. Oops. Let me just not do that yet. So concave down at 3, let's see if it changes directions. So let's choose a number bigger than 3. So how about x equals 4? Plug it into the second derivative. Well, 20 times 4 squared, that's positive. 4 minus 3 is positive. This is greater than 0. This is concave up after 3. So if it changes concavity, that means there's an inflection point there. There's only changing concavity between at 3. So this is an inflection point. So we need to figure out what is that x value. So we need to go back in and plug that into our original function to figure out what that value is. So if I look at f of 3, so I'm looking at 3 raised to the 5th power minus 5 times 3 raised to the 4th power. If you do that, you get -162. So we have this inflection point. The point's going to be at 3, -162. Okay, so this was 256. So -3, I'm just going to estimate right here. Or x equals 3, this is negative. 162. So that's where it's changing concavity. We're still concave down here. Trying to make it look concave down. And then we're changing to concave up, still decreasing. And then we're changing direction here, and it's always going to be concave up. Oops. We could go a little bit further by finding any intercepts. So x-intercept and y-intercept. Well, I can see we have one at 0, 0. If you look at your original function f of x, and we plug in 0, well, it makes sense we get 0. So that's our y-intercept, x to the 5th minus 5x to the 4th. If we set this equal to 0, we can factor out an x to the 4th from both of those terms. We get x minus 5. We're setting this equal to 0 to find our x-intercepts. And so it's when x to the 4th equals 0, x equals 0, or when x minus 5 equals 0, or x equals 5. So I know that it's changing direction here and should be crossing at 5. So technically, I'd have to change my graph a little bit to make that happen. But you get the idea, right? Okay, so putting together pretty much everything that we've been learning with first derivative and second derivative. So now we want to graph y equals the square root. Underneath the radical is 1 minus x squared. That's all in the numerator. And then that's all put over the denominator, which is the quantity of 2x plus 1. So I noticed we do have some trouble spots here. There are values which set is undefined, values of x that set my denominator equal to 0. So I know 2x plus 1 cannot equal 0. That's not in my domain. So if I solve for x there, subtract 1, divide by 2, I know x cannot be negative 1/2. I also know I have a problem because I have a radical. And that radical is a square root, so it's an even index, which means I can't have negative numbers underneath that radical. That would give me an imaginary number. It wouldn't give me back a real number. So I also know that what's underneath the radical, 1 minus x squared, has to be greater than, it could equal 0 because it's in the numerator, 0. So this is where you have to go back, kind of remember in algebra, if it was a nonlinear inequality, which this is nonlinear, this is where we had to find, we called them critical values there too. We had to find the values where it set it equal to 0. So 1 is 1 minus, and I can factor 1 minus x squared. So 1 is 1 minus x times 1 plus x equal to 0. This is when x is equal to 1 and x is equal to negative 1. So this is where this is going to be touching the x-axis. This is, think about this as actually a semicircle, right? And so we just need to test to see when is this positive, when is it negative. So if we plug in our values, negative 1 and 1, if you choose something to the left, so let's say x equals negative 2. We want to see, does that make this a true statement or a false statement? So is 1 minus negative 2 quantity squared, is that strictly bigger than 0? Which it's not, this is false. So I can't have this in my domain. If I choose something between negative 1 and 1, so how about 0? If I plug that back into this inequality, I want to show that it's true or false. So 1 minus 0 squared, is that bigger than or equal to 0? Well, that's true. To choose something that's bigger than 1, so 2. If you plugged it back into the inequality, it's false. 1 minus 2 squared is not bigger than 0. So our domain, I have to be between -1 and 1, but I cannot equal -1/2. So our domain, so this is going to be helpful later on. We're looking at -1 including, put it right in a world notation, -1/2 with a parentheses, union -1/2 to 1 bracket. Notice that the value that sets our denominator equals 0, x equals -1/2, it does not set our numerator equal to 0. And so we're going to have a vertical asymptote at x equals -1/2. We might as well just do it right now. Our x-intercept, well, that's when this whole piece is equal to 0. We already found that 0 is equal to the square root of 1 minus x squared all over 2x plus 1. If it's a rational function and we're trying to find when this is equal to 0, it's basically only worried about when the numerator is equal to 0. We could clear the fraction by multiplying both sides by our denominator, 2x plus 1. So 0 times anything is 0. So I would be just left with 0 equals my numerator, square root of 1 minus x squared. I could clear the fraction or radical by squaring both sides. Remember, if you raise both sides of an even of an equation by an even power, we could get what is called extraneous solution. So we got to be worried about that a little bit. So this is 0 is equal to 1 minus x squared. We can factor this. We can use a square root method. And this is when x is plus or minus 1. Okay, so these are our x-intercepts. So we have one at -1, 0, and 1, 0. The y-intercept, that would be plugging in 0 wherever we saw an x. And so if we did that, we would get the square root of 1 all over 1. So if we looked at the y-intercept, when x is 0, we get back 1. So we know we have points here, here, and at 1. We also know that we have some sort of asymptote at -1/2, vertical asymptote. Now let's look at where it's increasing and decreasing. And so we want to look at the first derivative. So looking at the first derivative, let's rewrite our function a little bit. Y is equal to, instead of the square root, we're going to write it with the 1/2 power. So 1 minus x squared, all raised to the 1/2 power, all divided by 2x plus 1. So for now, I'm going to just bring this up and let's just work with the derivative. So we got to use the quotient rule. And within the quotient rule, when we take the derivative of the numerator, we have to use this chain rule. So the derivative of the outer, so 1/2 of the inner, 1 minus x squared, subtract 1 from our exponent. So 1/2 minus 2/2, so that's -1/2, times the derivative of the inside. So don't forget about that. Derivative of 1 minus x squared is -2x, times the denominator, 2x plus 1, minus our numerator, 1 minus x squared raised to the 1/2, times the derivative of the denominator. So that would just give me 2. all over this denominator quantity squared. Okay, so I notice I have a complex fraction because I actually really have fractions within fractions. I don't like that. And I need to find when this equals 0 and where it's undefined. I can already see where it's undefined. That's when x is -1/2. That was originally the case, and we have a vertical asymptote there. I need to clean this up, like I said, so let's do that. I notice in this first grouping here, notice this -2 in front of this x, that's in the numerator where this 2 from the 1/2. So those are going to cancel. So let's leave it like that. While we do this, and this is a negative, let's distribute -x to each term in here. And so that would give me -x times 2x. So that's going to be a -2x squared. I have a -x times this +1, so this is just -x. This is all over, so I'm bringing this piece down to the denominator just for this. So 1 square root of 1 minus x squared. Then we have minus, I'm going to pull this 2 in front. So 2, and this is a square root. So square root of 1 minus x squared. And this is all over 2x plus 1 squared. So I can notice I can clear my complex fraction. I like to do it by multiplying by that fancy one. And that fancy one that I'm going to use the denominator, well, the fraction with inside this main fraction. So my denominator is the square root of 1 minus x squared. Square root of 1 minus x squared. So when I distribute, my fraction goes away there, and that's the whole point of that. So I'm just left with my -2x squared minus x. When I distribute it to this piece, notice I have a square root of 1 minus x squared quantity squared. So my radical goes away. And so I'm left with this -2 times parentheses what's underneath the radical, 1 minus x squared. All over this 2x minus, or 2x plus 1 quantity squared times the square root of 1 minus x squared. So let's distribute our -2 to the parentheses. So bringing down what we have, -2x squared minus x, -2 times +1, so -2, and -2 times -x squared gives us plus 2x squared. All over this 2x plus 1 quantity squared square root of 1 minus x squared. So notice a -2x squared and a +2x squared cancels. So we get that our derivative is -x minus 2 in the numerator, all over this 2x plus 1 quantity squared square root of 1 minus x squared. So we need to find when that derivative equals to 0. Well, again, that's only when we only have to worry about the numerator. So when is -x minus 2 equals 0? Well, if I add x to both sides, I get x is equal to -2. This is a critical number. The problem is this is not in our domain. The other values we had to look at is where it was undefined. So it was undefined where x can't be 1/2 or -1/2. And here we can't have 0 in the denominator. So x equals plus or minus 1. +1 and -1 are in our domain of our original function. So really, we're just looking at, here we have -1 on the left, but we can't choose anything smaller than that because that's not in our domain. We have to look at what's happening between -1 and -1/2, and -1/2 and 1. So we want to split this up into 2 different intervals. So choose a number between -1 and -1/2. So how about x equals -3/4? So again, we're only worried, is this positive or negative when we plug this in? So is 1 y prime of -3/4. If we plug that into the numerator, -x minus 2, that's going to be negative in the numerator, all over. Well, if you square anything here, that's positive. And here, this is positive. So we have a negative over a positive, which is less than 0. And so that tells me it's concave down here. Not concave down, it's decreasing. Same idea, choose a number between -1/2 and 1. So how about x equals 0? If we plug it in here, we get -0 minus 2. Notice that our numerator is negative, divided by our denominator, which is positive. So this is also less than 0. So it's decreasing everywhere. Is that possible? Because we found that it was equal to 0. Oh yeah. Okay. So I'm just going to show us what we have so far. So it's decreasing, and we have a point at -1, 0. So it's decreasing from -1, 0. And so it's going to be coming down here. My guess is that this is going to be a concave down piece. And then we also have that it's decreasing, and it's going through this point, and it's stopping here. So it's decreasing, it's coming down. This is a vertical asymptote. My guess is it's going to change concavity in here, but I'm not quite sure, and I won't know that until I take the second derivative. But we got things that are decreasing. So again, we can know more about that shape, concavity, but now we have to look at that second derivative. Okay, I'm looking at that function. My first derivative, I'm thinking, oh, we have to use the quotient rule, and we have to use the product rule within that. Okay, so I can cry about it a little bit, but I got to do it. So it's not bad. It's just a lot of algebra. So let's look at the second derivative. So when I take the second derivative, quotient rule, derivative of the top, derivative of -x minus 2, that's just a -1. So -1 times my denominator, which is that 2x plus 1 quantity squared, square root of 1 minus x squared. Minus my numerator. Notice if I distribute a negative to this numerator, I guess that would, well, let's just keep it. That would make it positive. So -x minus 2 times, this is where I have to take the derivative of the denominator. That derivative of the denominator, I need to use the product rule. And so, and within the product rule, I have to use the chain rule. So derivative of the first piece in the denominator, bringing down my exponent of 2 on the inside, x squared, or 2x plus 1. Subtract 1 from my exponent, times the second piece. So keep it as the square root of 1 minus x squared plus the first. So this, oops, did I take the derivative of the inside yet? I have not taken the derivative of the inside yet. So times the derivative of this inside, which is 2, all times the square root of 1 minus x squared. Plus, so the first piece in the denominator, this 2x plus 1 quantity squared, and the derivative of the second piece, I'm going to use the chain rule. So bring our 1/2 down. Yuck. The square root of, so of the inside, 1 minus x squared. Subtract 1 from our power, so negative 1/2, times the inside, derivative of the inside, which is negative 2x. Can I do it? And this is all over this denominator squared. So 2x plus 1 squared, square root of 1 minus x squared, quantity squared. This whole thing is squared. Okay. Now I have to look at when this numerator is equal to 0, where it's undefined. We already know where it's undefined. Looking at when this numerator is equal to 0. Let's think about this. Let's clean it up a little bit. This is, let's just keep the negative. Two x plus 1, quantity squared, square root of 1 minus x squared. So this is going to be minus negative x minus 1. Here we have a 2 times a 2, that's a 4. And maybe we can distribute that 4 inside the parentheses 2x plus 1. So that would give us 4 times 2x is 8x, and 4 times 1 is plus 4. Square root of 1 minus x squared. Here, this is where our 2's cancel. This is a negative. So minus. And then we're going to bring this down. So we have a minus, we have an x. We have this 2x plus 1 quantity squared all over the square root of 1 minus x squared. If I square this piece, this gives me a 4th power. And I can do this because it's strictly multiplication in between. And if I square the square root, that's going to give me a 1 minus x squared. So if we clear our fraction, hold on, I just need to make sure. This should be an x minus 2. x minus 2. And this piece is outside. Okay. So let's get rid of this complex fraction. Let's multiply by the square root of 1 minus x squared all over the square root of 1 minus x squared. When I distribute it to the first grouping in here, notice those are both square roots. So we get y double prime equals this negative 2x plus 1 quantity squared. And then square root times a square root, same thing underneath the radical, the square root goes away and we just have that parentheses 1 minus x squared. Minus x, negative x minus 2. So here, I'm just going to distribute it into the bracket piece, because that's where I want to clear the fraction. And when I distribute it to this piece right here, I am left with my 8x plus 4. But again, the square roots go away. And so I would just be left with 1 minus x squared in parentheses. When I distribute it to the second grouping here, the square root goes away, and I'm left with that minus x all times that 2x plus 1 quantity squared. All over our denominator. So 2x plus 1 to the 4th, 1 minus x squared times the square root of 1 minus x squared. And it doesn't look like there's much that we can clean up. So it would be distributing and combining like terms. Which I know we can do this, but this is going to be, this is going to take us the rest of the class period. Was there a way that we could have done this a lot easier? I'm not sure. And watch us, we probably won't even find, let's just use for now, watch us find that any number we have was outside of our domain. Let's just look really quickly. If this was -1, this is -1/2, and we have 1. Only thing I might see that it would maybe possibly 0, but I'm not sure. Because looking at this, okay, let's just do it. So let's choose a number. Actually, I can't because I need the second derivative, don't I? I'm just trying to make it life a little easier. But I don't see how. Okay. Right now, I'm going to distribute out 2x plus 1 times 2x plus 1 quantity squared. If I do that, that is 4x squared. That would be a 2x plus a 2x, so plus 4x plus 1. And at the same time, I'm going to distribute this negative to the second parentheses. So that gives me -1 plus x squared, or x squared minus 1. I can distribute this, and let's just not distribute it. So this is, actually, let's distribute it. So this will be a positive now, parentheses x plus 2. Inside our bracket, so let's go ahead and distribute and combine like terms. So if we distributed 8x plus 4 times 1 minus x squared. So that's going to give me 8x minus 8x cubed. Doing the 4, that would give me plus 4 minus 4x squared. Minus x, and now I need to FOIL out 2x plus 1 times 2x plus 1. So if I did that, that's 4x squared plus 4x plus 1. And I'm going to just put denominator here. I don't care about the denominator. So I need to distribute. So 4x squared times x squared is 4x to the 4th minus 4x squared. 4x times x squared, that's 4x cubed. 4x times negative 1, that's negative 4x. I'm now distributing the 1. So plus x squared minus 1. Plus x plus 2, all times. Let me just rewrite this piece with distributing the negative x. So this would give us a negative 4x cubed. This would give us a negative 4x squared. And this would give us a negative x. So let's combine what we have, like terms. So let's start with the cubes. I have a negative 8x cubed minus a 4x cubed. That's a negative 12x cubed. I have a, let's go to the squares, a negative 4x squared and a negative 4x squared. That's a negative 8x squared. And then any terms with x. So we have a negative 8x and a negative x, or sorry, positive 8x and a negative x, so that's plus 7x. And then any constants. Only constant I see is plus 4. So I'm going to combine like terms right in here. So bringing stuff down, I have a 4x to the 4th plus a 4x cubed. Here I have a negative 4x squared plus an x squared. So this is minus 3x squared. Minus 4x plus 1, or minus 1. And now we need to distribute still. So this is going to give me a negative 12x cubed, actually 4th, minus 8x cubed plus 7x squared plus 4x. Distributing my positive 2, I get negative 24x cubed minus 16x squared plus 14x plus 8. All over the denominator. Almost there. We need to combine like terms. So we have a 4x to the 4th. That's only x to the 4th term. Nope, there's a negative 12x to the 4th. So that's a negative 8x to the 4th. Looking for my cubes, I have a 4x cubed, a negative 8x cubed, that's negative 4. Negative 4 minus 24, so that's negative 28x cubed. Looking for my squares. negative 3x squared plus 7x squared, that's 4x squared. 4x squared minus 16x squared, that's negative 12x squared. Looking at any terms with just x, I got a negative 4x plus a 4x. Those cancel, plus 14x, plus 14x. And then we have negative 1 plus 8, which is plus 7. And now we need to figure out when that's equal to 0. I can use my rational zero theorem to see if there's any rational zeros, but I notice that I'm going to have to go through and look at fractions and then long division or synthetic division, and we're already out of time. So let's plug this in, and I wouldn't give you one this hard or long on the exam. So let me just plug that into Desmos. So let me just pause the recording for a sec. Okay, so first thing I did was I pulled up Desmos and I looked at when our numerator was equal to 0. And so looking at the graph of the numerator, I can find that it's equal to 0 when x is negative 2.7. Well, that's outside of our domain, so we don't have to worry about it. Also, when x is negative 0.916, when x is negative 0.5, that's where our vertical asymptote was, so we didn't want to worry about that. It wasn't defined there. And x equals 6.89. So these are possible inflection points at negative 9.16 and at 6.689 if I did all the algebra right, getting that numerator. So then the next thing I did was not look at that. Let's look at the graph that we wanted to graph. And so this was pretty much what we had gotten before. We had seen that we had x-intercepts at x equals negative 1 and x equals 1. We saw that it was a decreasing function and we had a vertical asymptote at x equals 1/2. And so notice there's a vertical asymptote here at x equals negative 1/2 on both sides. We saw that was strictly decreasing function. And it looks like that there's a slight, that this is concave up and then down. And so that should be where we get that negative 0.916. The other place where we saw an inflection, so notice that this is concave up until we get to about 0.689, which we saw was the inflection point. And so we were going about this right. It was just a lot of ugly algebra and not enough time in the class period to finish. But we had gotten that general shape of that graph, which was right here. Okay. Okay, so that is it for today. But I will stick around if you guys have any questions. We can go over any problems you want to go over.